Welcome to week 6 of our course. In the last week's lecture, we have seen the concept of connectedness. So recall that we have seen connectedness of topological spaces, and in particular we proved that every closed interval in the real line in R is connected, because it was we showed this result in much more generality of that of the linear continuum, and of course R is a linear continuum, so every closed interval in R is connected. Now, using this connectedness property of closed intervals in R, we have the notion of a path in a topological space. So let me give the definition of a path, and with that notion we can define what is called path connectedness. So what is a path? So let us define a path. So suppose that X is a topological space and X and Y are 2 points in X. So a path in X joining X and Y, or we can also say a path from X to Y. Okay, so we can use both these terminologies for a path. So what is a path in X joining X and Y, or a path from X to Y? It is a continuous function f from some closed interval AB of the real line to X. So AB is closed interval in R, such that f of A equals X and f of B equals Y. So this is called a path joining 2 points X and Y. So you can think of a path, let's say this is X and this is Y. So you can think of a path as some kind of curve, continuous curve that joins these 2 points. So now the direction of this curve goes from X to Y. Okay, so it starts from X and goes to Y. So this is called a path from X to Y, and this curve is precisely given by the function f. So now we can define what is path connectedness of a space. Path connected space. So topological space X is called path connected if there exists a path between any 2 points of X. So any 2 points in X can be joined by such a curve. Now immediately from the definition we have the following lemma. So because our closed interval AB is connected, we can easily state this lemma, which says that a path connected space is connected. So let's see a quick proof of this lemma. So suppose X is path connected but not connected. So again, by contradiction, we will argue by contradiction. So if it is not connected, then there exists a separation AB of X. So AB, as you remember, these were non-empty open subsets of X which were disjoint and whose union is X. So if it is a separation, if you have a separation AB of X, now you can use the connectedness of the closed interval AB. So since AB is connected, any path F defined using this closed interval AB to X must satisfy F of AB lies either in A or F of AB lies completely in B. This is because F is continuous. So we have seen that continuous images of connected sets are connected, and if you have a separation, then any connected subspace of X must lie either entirely in A or entirely in B. This means that this implies that there exists no path from any point in A to any point in B, which is a contradiction since X is assumed to be path connected, and the union of these two sets A and B is the whole space X. So this is a contradiction. So we see that any path connected space must be connected. Now, before we go to further properties of path connected spaces, let me give a few examples of path connected spaces. So our first example is that of open or closed Euclidean balls in Rn, and these are path connected subspaces of Rn. So how do you prove them? Prove that these are path connected. So suppose you take when I say open or closed, so they are of two types. So either you have BDXR, which is, as you remember, these are the collection of points in Rn such that dx x prime is less than R. So here x is any point in Rn and R is positive. Okay, and if you write the closure, so the first one is the open Euclidean ball, and the second one, the closure, is the closed Euclidean ball, and this is precisely this the points in Rn for which dx prime is less than or equal to R. Okay, so both these sets are path connected. So let us try to show this. So take any 2 points x1 and x2, say, in the open ball with center x and radius r, and now we have to define a path that starts, let's say, at x1 and ends at x2. So for this we define the function f from the closed interval 0 1. So here we are taking a to be 0 and b to be 1, and this is a function from 0 1 to, say, Rn, which is given by f of t is equal to t times x1 plus 1 minus t times x2, and in geometrically this is nothing but the straight line joining 2 points. So suppose this is a point x1 in R2 and x2 in R2, then this function f defines the straight line ft. So this for some t, this is the point ft will lie in the straight line joining x1 and x2. So now I claim that first of all that f0 equals equals x1, sorry, x1, and f1 equals x2. So it is a path, sorry, it should be the other way around. f0 equals x2 and f1 equals x1. So it is rather a path that starts at x2 and goes to x1, ends at x1. So this is immediate from the definition. Okay, so this is immediate from the equation above. So if you just plug in t equal to 0, then this part vanishes and this part is giving you 1, so it's just x2. And if you plug in t equal to 1, then this part vanishes and this part will give you x1. So this is immediate. Now the next claim is that ft belongs to bd xr for all t in 0, 1. So this is required because the definition of a path connected subspace should have that the path itself that joins 2 points within a subspace must lie within the subspace for all points in the enclosed interval on which it is defined. So here, if x1 and x2 are 2 points in, say, some circle that contains both these with center x and radius r, then the line joining these 2 points, I'm claiming that this lies within this open Euclidean ball. So let's see a quick proof of this fact. So what we will do is try to compute dftx, and we will show that this is less than r. So for all t in 0, 1. So what is dftx? This is nothing but tx1 plus 1 minus tx2 x, and if you remember, this is nothing but the norm of the difference of these 2 points. So what was the norm? So norm of an element a in Rn was just the sum of ai squared, I equal to 1 to n, and with the square root sign. So this is just the Euclidean norm, and we define this is nothing but the distance of a from the origin in Rn. And so the if you take any 2 points, let's say a, b, this is nothing but the norm of a minus b, and you can directly check this from the definition of the Euclidean norm and the definition of the Euclidean metric on Rn. And now once we have this expression for the distance between ft and x, then we can use the triangle inequality for the norm that we proved earlier. The triangle inequality for the norm said that if you have 2 points a and b, then the Euclidean norm of a plus b is less than or equal to the Euclidean norm of a plus the Euclidean norm of b. So now if we use the triangle inequality, using the triangle inequality, we get that the distance between ft and x, which was nothing but tx1 plus 1 minus tx2 minus x, and this can be rewritten as t times x1 minus x plus 1 minus t times x2 minus x, just by writing x as tx plus 1 minus tx. So you can just check that you can break x into these 2 parts and take them join them with x1 and x2, these two parts. So now I can use the triangle inequality, and this gives us t times the norm of x1 minus x and plus 1 minus t times the norm of x2 minus x. And remember that this was nothing but the distance between x1 and x, and this was nothing but the distance between x2 and x, and so these are both less than r by definition, because they are both in the open Euclidean ball of radius r with center x. And so this is less than, so let me write it in a new line. So this is less than tr plus 1 minus tr, which is nothing but r. So we see that the distance between ft and x is strictly less than r, which means that, so, and this is for all t in 0 1, which means that ft belongs to the open Euclidean ball with center x and radius r for all t in 0 1. So we see that the open Euclidean ball is path connected. BDXR is path connected, and a very similar proof will also show that similar argument shows that the closure BDXR closure is also path connected. Our second example is that of a punctured Euclidean space. So what is a punctured Euclidean space? It is just the space Rn minus some point. So you're removing one point, and that's why it's called punctured Euclidean space. And I claim that this is path connected for n greater than 1. So n greater than 1 is important because if n equals 1, for example, if you take the real line and let's say you remove the point 0, so this point is removed, then there is then this is a disconnected space. Okay, so R is not connected, R minus 0 is not connected. So one can simply show that these two open sets, so minus infinity to 0 and 0 to plus infinity is a separation, and so it is not connected, and therefore it is not path connected, because path connected spaces are connected. So it's just the negation, or rather the contrapositive of this statement. So if R minus 0 is not connected, it is not path connected. However, when n is greater than 1, it is path connected. So to visualize this, let's take R2. In R2, and you are removing the origin, let's say, so I'm taking A to be the origin here. Now if you take any two points, say one here and one here, then it might be that the line joining these 2 points does not cross the origin. So if the line, straight line joining x1 and x2 does not, so this is R2 minus 0 0, okay, so it does not cross the origin, then we can just take that path, then that path joins x1 and x2 in the punctured Euclidean plane, which is the case for 2 dimensions. So however, it could happen that the straight line joining these two passes through the origin, but we have enough space, so we can take another point, let's say x3 here, which is not the origin and different from these 2 points as well, and it has something that does not lie on this line. Okay, and then we can join x1 to x3 and then x3 to x2. Okay, so we go from x1 to x3 by the straight line and then join x3 to x2 by another straight line, and that is a path. Just by using the pasting lemma, we can show that this now defines a path between x1 and x2. So here if f1 is a path from x1 to x3 and f2 is a path from x3 to x2, so we have seen that if the origin lies in this line, say L, on L, then choose x3 not lying in L and join x1 and x3 and x3 and x2, and then the path, the concatenation of these paths give the required path. So it joins x1 and x2. So this is a visual proof of the fact that R2 minus the origin is path connected. So as an exercise, first of all I want you to make this argument rigorous. So as an exercise, make this argument rigorous, which means that you have to write down all the equations. Write down all the equations and justify things. So one thing that has to be justified is how to check that the concatenation. So by a concatenation I just mean that first you traverse this path and then this path. Okay, that's just a concatenation of two paths, which one ends at x3 and the next one begins at x3 as well. So you can just join them. So I want you to write down all the equations and prove that the concatenation is continuous, for example. So it actually defines a path. Now let us see another example of a path connected space, and this is given by the unit sphere Sn-1. It is denoted as Sn-1 in Rn. So what is Sn-1? It is the set of all points in Rn with norm exactly equal to 1. So for example, if n equal to 2 in R2, this is nothing but the unit circle. So it has center 0 and radius 1. If n equal to 1, then it is nothing but the just 2 points. It is just the union S0 is just the union -1 1. So this is not connected, and so not path connected. And so here again we need to restrict to the case n greater than 1. So these is path connected. So here we cannot use the previous argument that we used for the for example the open Euclidean ball, because our if you take 2 points, let's say here and here, then the straight line joining these two will not lie on the circle. So we have to find another path, which is just the path that traverses the circle in the case n equal to 2, and it should always lie on the unit sphere. So for this we will use the previous example to prove that this is path connected. So consider the function g, which is from Rn minus 0 to Sn minus 1, and this just takes any point x and divides it by the norm. Okay, so then the norm of gx is equal to norm of x over the norm of x whole norm, and this is nothing but the norm of x divided by the norm of x, and this is equal to 1, and this is well defined because we are excluding the point 0. So this function g this is a continuous surjective map from Rn-0 to Sn-1. And now we can use the fact that Rn-0 is path connected, and so Sn-1 is the image of a continuous map from a path connected space. So Sn-1 is an image of a continuous map under on a path connected space. And just as we proved that the image of a continuous map of a connected space is connected, we can also show that the image of a continuous map on a path connected space is also connected. So Sn-1 is connected. So here I leave this as an exercise to show that continuous image, by which I mean the image under a continuous map. So continuous image of a path connected space is path connected. So prove this fact using the definition of path connectedness. You can easily show that this is true. Okay, so we have seen some examples of path connected spaces, and now we can try to see some examples of spaces which are not path connected, and even examples of spaces that are connected but not path connected. We have seen that path connectedness implies connectedness, but the converse is not true, and we will see a couple of examples in the next lecture.